Okay. That's good. Okay. Howdy, folks, and we are live. Just about 1 minute from the start of our class. Okay, we're on, and I don't see, and I have some viewers, so welcome to, probably should turn back to the title slide, and welcome to Constraint Handling Rules. This is going to be pretty much a traditional lecture this time, in which I will present some new material, and we will start looking at constraint handling rules. Constraint handling rules is a system originally by Tom Fruworth, that has been worked on by many people since then and has actually become fairly widely used. It involves putting objects called constraints in a constraint store. So here's our constraint store, and here's some constraints in the constraint store. Now, the cool part is we can have rules. Here's a rule. When I see a green diamond and a red heart in the store, add a yellow sun. Let's see how this works in practice. Here we go. I've got a rule. I will add the green diamond from Prolog. Now I have the green diamond in the store. I now have I will add a red heart from Prolog, and now our rule fires, and we add a yellow sun. Okay, questions about this? Is anybody out there? I'm not hearing anybody. Can people hear me? Somebody tell me if you can hear me, because I'm not getting any feedback. It is indeed Thursday. I'm not on the wrong day. There are people watching. Okay. All right. This is all making sense to you? Good. I'm realizing this may be a little quick. I'm going through this a bit fast. Okay. So now, the rule fires, and okay, great. All right. Here we have added our red heart. That's where we stopped. Now the rule fires and adds the red sun, and that's what we're left with in the constraint store. This stable state is called a solution. So this is generally what happens if you add something to the store, then it sort of runs for a while and eventually reaches some stable state. And it's in fact, if you visit the CHR Museum in World, you will find the little exhibit with the button puzzle game that shoots out boxes, and whenever you put something in the store and rules start firing, then it makes particles, and eventually it'll stop making particles, and the store will reach some stable state again. Do visit that in World. Okay, so this kind of rule is called a propagation rule, where you see some things in the store and you add something. Now, let's add another kind of rule. When a flower and a heart are in the store, replace them with plus sign. Or cross. Guess I'll call it a cross. Okay. From Prolog, I will add the flower. Starting with where we were. The rule fires. And now we have the cross and the heart and the flower are gone. There's another kind of rule available to us, a simplification rule. This is obviously a melding of simplification and propagation. So when a stop sign and a heart are in the store, replace the stop sign with a flower. That's a rule. And I guess I should say, notice that the heart will remain. So Prolog adds, we add a heart externally from Prolog. And we add a stop sign. And now the rule fires. And the flower gets added and the stop sign goes away. But now, remember we had this other rule. When there's a heart and a flower in the store, replace them with a cross. But here's our store at the moment. Hey, there's a heart and a flower in it. So the simplification rule fires. The heart gets deleted, the flower gets deleted, and we get another cross. Notice it's another cross. We can have multiple copies of something in the store. And here's our final state. For CHR, the syntax looks like this, where it's callable. Any of these symbols could be replaced by a callable. And the right-hand side, in particular, can get quite a bit more complex. So you can set up a guard if it's as simple as, like, if you want something like, if you see a green diamond and a red heart, give me a yellow sun, but only if it's Tuesday. And you can also call Prolog on the right-hand side. So this is kind of a nifty system. You can do a lot of things with these kind of rewrite systems. And that's what this is. This is a rewrite system. Okay. So, boy, I'm realizing just how much this is going to be short, because I didn't expect to go through these slides this fast. Okay, this is that feared thing by all programmers, state. So let's hear from you. What's bad about state? I mean, we don't have any Haskell fanatics in the room tonight. Nobody's going to rant about state. Oh, people are beginning to rant about state. Adrian, what's it mean it always goes to an unpredicted state? You need memory. Well, you are going to need memory to keep state. But I think that's pretty unavoidable. State's mostly a problem if you have some kind of concurrency. Yes, we will talk about threads and concurrency and state. Any other problems with state? Yeah, you can end up in states you never thought about. So you can end up with invalid state. And it's always better to be unreproducible, or unexpressible. So, but that can be hard to do. Okay. Let's talk about state and some of the ways people attack it. I have this I sometimes think that people's way of attacking the problem of state is either to kind of go, oh yeah, it's state, we have to have state, or you have people who go, no state, no state, no state, no state, which is but few people kind of put it front and center and address it, and I kind of like that about CHR. It's like, yep, we're stateful, we're going to do it the right way. Werner says, what I meant with memory, you need to reason over many possible states. That's a good point. You can end up, you just have these variables and you don't really have a way of saying, and they should always maintain this relationship. But you can do that with CHR. You can say, well, when you get to this state, when you have this thing in the constraint store, you should do this, right? I never want to have a flower and a heart in the store without, or I never want to have a heart and a diamond in the store without having a sun there. That could be something much more practical, like I never want to have an item and a price in the shopping cart without also having a quantity. Okay, state bad. So why are we looking at something that's got like state written all over it? Well, because state may be bad, but we're kind of stuck with it. Yeah, thread. Somebody mentioned concurrency. CHR is one store per thread. So it will give you, so in that sense, externally, you don't have to worry about concurrency because whatever thread you're on is the store you're in. On the other hand, the CHR resolution algorithm is extremely parallelizable and will take advantage of that. Okay, somebody mentioned having lots of states you never thought about. Yeah, a similar thing is that when you have state, then you can have things that aren't in sync, like a model and a view, and the view is not in sync with the model, or you have things like you try and make your web page snappy by doing optimistic update, and then it fails, and now you have this complicated, messy problem because then somebody does something else, and only now do you get the update. So that can get really complicated. And finally, state seems to mess up any attempt to have mathematical elegance of any sort. I should say that CHR is quite mathematically elegant underneath. It has properties like being online. You never have to kind of accumulate inputs before you can continue to process. You never have to, it's anytime. You never have to, you can stop at any point and then resume the computation. And it's, okay, so, and for many CHR programs are confluent, which means the order in which things fire it is not important, and many are concurrent. That is, you can parallelize them. Okay, so ways of dealing with state. Well, one, objects are actually kind of a way of dealing with state. You wrap the raw state up in a model, and oftentimes you can kind of use this encapsulation to deal with the thread problem, and to use events to make certain that views get updated. But what are some problems with OO? I'm certain many of you have day jobs doing OO. What's some problems with OO? And I'll wait. The state's shared. Hang on. And Norbert says the state is shared. Yeah, whoever has a reference to the object can modify it. Yep, it's kind of anarchic that way. Okay. One other. So, yeah, everything gets wired together. That's essentially that's a related issue that pretty soon you've got all kinds of things modifying the state, and it's a bit of anarchy. And one attempt to put some order in that is inversion of control. The only problem with inversion of control is that in practice it becomes a mess to work with. Okay, probably most of you have less experience working with agents. Norbert may be our exception here. But for 4 years, my primary language was an agent language. Yeah, unless you have transactional memory. But yeah, if you have transactional memory. Agents. Agent-based systems essentially give a thread to each object, and the objects only communicate by passing messages that are queued up. So Erlang, yes, if you have transactions in Erlang, then this is an attack on this, right? So Erlang is Erlang's is closer to an actor language. No, my primary language for 4 years was LSL. It's actually the little scripting language for that all of the sort of automated stuff in OpenSim uses. Okay. So now we can make the object kind of self-contained, because the only thing that comes in and out are messages, and this really solves the thread problem and a lot of the coupling problems. But it becomes very difficult to kind of make verb objects. Doing something like making a sequence of things involves making a bunch of objects and then having each one kind of fire off the next one, and that can get really awkward. Then there's functional programming. Monads. Monads. Monads kind of are sweeping state under the rug. Really, when you kind of scrape away a lot of the math, the state monad is the same thing as sweep prologs, just pass everything around on the stack. So CHR says, well, quit worrying about threads, make your world signal threaded, and use multiple threads. There are still non-pure functional languages like Lisp. There are. Yep. And yeah. One other bad thing about monads is just that that they're really hard to think about. So I kind of like CHR's model. It's an interesting attack on the notion of state. Hey folks, and my streaming software is yelling at me that it disconnected and then reconnected, but I think we're back. Okay. Somebody says OO is verbose, and I'd agree with that. It can make understanding, and Anthony on the YouTube says, can make understanding and reasoning difficult. Used to rant when using Spark Ada. We really controlled state to enable control correctness proofs. And hang on, somebody on the Slack. Video wasn't interrupted. Okay. Who knows? Well, so yeah, Anthony, can make your understanding and reasoning difficult, definitely. And I suspect you're talking about you may be talking about inversion and control there. Okay, so that's what I had to say about. So but I guess I will. So I'm going to talk about, so I'm done talking about CHR and state, unless folks have other comments. I must confess, I went through this much faster than I expected. So you know, I think I'll go ahead and go in world and get rid of this, and I'm going to do the get foo if I've been standing here for a while and maybe half disconnected. Nope, I'm not. Although, hang on, I also want to check and make certain that we're seeing enough of me. We are. Okay. Whoop. And it's a little hard to be in world. Okay. I'm going to talk about the get foo pattern because we're running short. So, okay. If you put things in the store, eventually you're going to want to find out what's in the store. And CHR actually is kind of awkward for that. So there's a pattern. CHR is definitely not Prolog. CHR is its own language, and so when you put something in the store, it can have a variable, an unbound variable, but what you're really doing is matching against something with an unbound variable. So to get something out of the store, you have to pass in an unbound variable, and then get it to bind that variable inside in the CHR. So here we go. Okay, I have some foos. These white cans are foos. And I'm going to define some constraints. We have, hang on, I will get this nice and big. Okay, here we go. Whoop. So we have a constraint called foo. Well, I'm going to need no less than 3 other constraints to get the list of the foos out. The first is I will have a thing called one foo, which represents a single foo. And then a thing called collect foo, which is going to be a repository for the list as I build it up. And then get foo, which is the actual constraint I put in to fire the whole thing off. Okay, so let's call loadit, which is going to add some constraints. You'll notice here we are. We've defined some constraints, and now all we have to do is call them like Prolog goals, and that adds them to the repository. Okay. Now, they might fail internally, but essentially, if you add them, they will be there. If you backtrack, it will actually undo it, but it's a committed choice. Okay, so how can we get these things out? Well, we have to do a little bit of shake and bake. Okay, we will add getFoo, the purple cube, and we will give it an unbound variable, which of course we'll share back out. So that's how we're going to communicate the final list back out. Okay? All right. So here I'm going to call go, and then that's going to call load it to just load the store up, and then calls get foo. All right. And like I said before, we're going to have when you add a constraint to the store, it's active, things will go on, and then eventually it'll settle down. And that's what we're hoping will happen here. And we're hoping in the settled down state that X will be bound to a list of all the arguments for foo1. Okay, so step one, we'll make a copy of our constraint. And then what we're going to do is we're going to destroy the copies as we collect them up, so we know we've collected them. Okay, and by the way, yeah, if you don't need the constraint after that, you can omit that step and just work directly on the originals. Okay, here I've made a propagation rule where I've said if you see a foo and a get foo, then add a one foo. And so that will be applied 4 times. It'll be applied once for 1, once for 2, once for 3, and once for 4. So here we are getting a set of duplicate constraints. The next thing we're going to do is get rid of getFoo and replace it with a collector. So, okay, here we go. Just replace getFoo. This is a simplification, so we're going to get rid of getFoo, but we're going to replace it with collectFoo with the same argument. The reason we need to do that is we want to stop this first process of copying things and start the process of picking up the copies. We make it a second rule so that as long as there are foos around that we haven't done this to, we're going to keep firing the first rule. So we get all of the possible ones, and then when otherwise it would have to stop, it would go ahead and call this second line, and CHR works going downwards. And if you haven't done the tutorial yet, I know I just put it out a day or two ago. Some of this may seem like a bit like magic, but the tutorial does a pretty good job of explaining it. I would say this week's a little funny between, half of us being in a country that's blowing up and your instructor blowing up, and so we're getting a little late start, and basically don't panic or be too anal about getting every last detail of CHR this week. Okay, because there's quite a bit of detail in that tutorial. All right, so now here we are. We've got collect foo. Now we're going to bind collect foo. We're going to take collect foo and one foo. Here we go. And we're going to get rid of both of those, and then we're going to put a collect foo back. But we've got a little bit of Prolog in the right hand side this time. So we get rid of one foo and we get rid of collect foo. But the new collect foo we make is going to pass the tail of the list. This is going to be a difference list or a whole list. The first element is going to be whatever we got out of one foo, and then we're going to bind that actually to whatever came in collect foo. So since we do that recursively, we're going to build up a list starting at the head and going to the tail, which we can do with a difference list. So here we are, we got one, and then we got like an unbound variable again. And now we still have one foos, we still have some yellow ones, so we'll get rid of the second one, call the same thing, and now our list gets longer, but still has a hole at the end of it. And is everybody following along? Are people happy? Let's do some baffleometry here. We're munching away at this list. And remember, the head of this list is still unified with L. So eventually the list is going to get passed back out. Not seeing anybody yelling at me to stop, so I'm going to keep talking. Okay, and finally we get to where we're out. We consume number 4, and at that point we can get past this one foo collect foo rule. Am I getting a cursor here? Yeah. Okay, one foo collect foo rule, and that won't fire because I don't have a one foo anymore. So now we take collect foo and we just take the tail and we unify it with the empty list, which will close off the list and make it a normal list. Okay. For those of you who have not visited the museum, you can see it's kind of behind JWU back here. And there's lots of fun things. There's a robot. There's some robots to play with. And some things about the history of CHR. And, okay. I have updated Rampaging Robots. So if you want to see if you're understanding CHR basics and you're retaining stuff, go jump in the rampaging robots and see if you're doing okay. All right, you are happy. You're H-Jappy, and I am Pfannenkuchen. I am H-Jappy. So, okay. How many of you have started the CHR stuff? Let's have a show of hands. Good. Norbert, how are you feeling about the CHR stuff? And Charles. Good. My experience with CHRs is a real simple idea with lots of little details and edge cases that can bite you. CHR seems very similar to Clips. Yeah, it's a forward chaining. It's a forward chaining system. It's a forward chaining committed rewrite system. So it's a lot similar to like an expert system shell. Good. I'm glad the exercises are working. I'm a little worried because that's the newest tutorial, and usually it takes a while for me to kind of figure out what works and doesn't work and clean them up. All of the tutorials kind of constantly are getting small improvements. And sorry, I'm not looking at people, but that's because I'm trying to read your comments. And that doesn't work either. Made it through a few exercises. Yeah, it's definitely back into the mind-bending area, and we're going to be in mind-bending space for the rest of this course. So far, we've been pretty much out of mind-bending. Planning was a little mind-bending. The web stuff was hopefully pretty straightforward and not very theoretically interesting. But we're back firmly in mind-bending. What's the strange sentence in the tutorial? Maybe I can explain it. Okay. I would say you can probably skip the chapter on constraints for now. I will put in the assignments that you should go back and revisit that after next week when we do CLPFD. Norbert, what can happen is you know what's going to happen with each rule, so you actually can know which rules are going to fire first, and it is possible to essentially make something that's not unlike like a table plan for SQL. You can kind of make an execution plan. There's a great deal of academic literature, much of it quite dense, I'll warn you, that discusses concurrency in CHR. And I'll be really honest, much of that's just beyond me. The academic literature on CHR is not as particularly, it seems, kind of unhelpful. It's pretty abstract. One reason I wrote the tutorial was that I write those things because when I need them. It is dependent. Medium complex areas where this would be used. Yes. I tell you what. Let me get the. There's an entire chapter in CHR of just examples. So let's just talk about some of those. Okay. That could just be like some problem. These things are written in ASCII doc and converted. What happens if the prolog in the body? Okay, I'm not certain what that intended was supposed to be. That does look like it. Okay. So what happens if you put some prolog in a CHR body? I know what this thing was supposed to say. Okay. I suspect strongly that's a problem with the markdown. What happens if the prolog in the body leaves a choice point? Well, you will have a choice point when you get back to prolog, and it can actually back up and go into that choice point. That probably should have read, then the original calling prolog sees a choice point. So calling a CHR constraint could be non-det. It could be non-deterministic. If the prolog inside a CHR won't make choice points and won't backtrack, but prolog that's embedded in it might. So, for example, if you made a CHR constraint that passed in an unbound variable, and then that unbound variable was the first argument to member with some list, you could do the sort of normal backtracking into member, even though it's buried in the body of a CHR constraint. It can also fail, by the way. If you fail in a CHR constraints body, then it will back out to the. It will undo all the changes you've made to the store, back out, and get you back to the prolog, which will fail. Okay, I'm going to answer Norbert's question. Medium to large examples. Let me find some. Okay. And again, I'm just going to talk about some things off of the tutorial here. Okay. Here's an example where I know of some CHR implemented things that do this kind of design constraints. You usually would not want to design an electrical circuit that had a short. Here's a bit of a CHR program, and if you hold two pins that are connected at two different values, which is what a short is, then you know that will have a short and we'll add a short to the constraint store, and then presumably that would be collected with get foo and get and displayed somehow, or we could just fail instead of adding that short. I know of a commercial application of CHR. One of the kind of larger and longer lasting ones is used to design injection molding molds and make all of the and make certain that all of the many constraints that have to be done with that are appear there. Hang on, I'm just realizing I'm no longer watching and now you're reading my email. Nope. Where did my, sorry, I've lost it here. Boom. Tutorial. There we go. Okay. So that's a kind of application, is to do that kind of constraint checking. And in the case of the injection mold, it's things like the water channels must not intersect with, there must be a route for the water. You know, you must have enough water channels for water to flow through the thing. The water channels must not intersect with the mold cavity, and so on. This is the code for a button, a GUI button. That's actually a pretty complicated thing that happens when you click a button, right? When you click the button, its appearance changes to the down position, and then maybe your hand moves a little and you get off of the button. Well, then you have to have some kind of like liminant state appearance. And if you drift back on, then you have to go back to the down appearance. And then oftentimes when you let go, well, if you're off, then you might have one animation. And if you're on, then you maybe have another one. Quite often that is an animation, so there's a couple intermediate steps. And then finally it goes back up and you send the actual event out. So this gets, you know, just a little crazy. And here's some code to implement a button. I've actually thought that a way of getting more people interested in logic programming would be to build a kind of game maker system using CHR. And of course you'd want to hide the crazy syntax and all of that. But games are about things changing into other things, right? You have a spaceship and you shoot at the spaceship, and now you have a damaged spaceship, and then the damaged spaceship blows up and becomes a wrecked spaceship, and this is a pretty good thing for CHR. You know, do we have a rocket that's intersecting with the spaceship? Oh, then the spaceship takes damage. Is the spaceship seeing the player's spaceship? Then it shoots at it. That kind of thing. This is also true for complicated GUIs. In fact, I'm really interested in kind of building some extended. Sounds a lot like state machines. You can implement state machines in CHR pretty easily. You know, you would just have a state constraint, and you have a rule that says if you have two state constraints, get rid of the old one, which you can do. There's a thing in here, set semantics. And then probably you have like an input constraint, and when you put in the input constraint, then it takes, then you have rules that define the state machine. You have I have this input and I'm in this state. Well, then retract both of those. It's simplification rule. And then make me a new state. You can also do composed state machines. Yes, you can. You can do hierarchical state machines. And for what it's worth, this is also a good way to implement behavior trees. So, okay. Imagine that we have a gigantic database of chemical reactions. And now I want to know what happens when I put some of this and some of that in. And CHR does kind of act like chemistry. You put things in and it changes into other things. You can write an interactive fiction game of the sort of go north. You are now in the king's palace, and there is a golden throne here. You could build one of those very, very simply in CHR. Darn, I forgot to start it. I was going to have that available. Apple's auto layout. Is that done in CHR? I didn't know that. I worked on the original theme editor. I was the contractor on it. Apple was not that friendly to AI-ish things when I was there. I did some stuff in Lisp, and everybody was like, "Ooh, and he's working in Lisp." I did run in XML, but XML wasn't around yet. Okay. You can do parsing, especially like bottom-up parsing, which is really useful for natural language processing, where people do make grammatical errors all the time, because you can do something like this. Take a you may have some ungrammatical sentence, but it contains big green bunny, and you can still understand that big modifies green bunny, which and green modifies bunny, and this whole thing is what do they call that? A noun phrase. So I want to order a big green bunny, and I want to order is probably something you hear a lot if you are like running a chat bot that takes orders. So with CHR you could discard the A, because often articles are just not worth dealing with in natural language processing. So Uh, Let me think. Okay. Here's an application. It's pretty easy to build a computer vision system to recognize a window. There's enough like little characteristics that are unique to windows to recognize them, and probably for doors too. But houses are actually kind of hard. So if I want to find a house, sometimes it's easier to go, well, there's a door and there's a window on either side of it, and hey, maybe this thing is a house. So that kind of recognition where the individual pieces, especially it may be difficult to know whether that's a window or a door. I mean, I've seen architectural features that I wasn't certain myself whether that was a window or a door. But, there's squares and there's other squares, and they have this nested relationship, and that makes a house. Another recognizer is it? Let's see. Is this used for finding decision? As in, have I found a house? Sorry about keeping on looking up. I'm using a large monitor. Oh, to make a decision about a business procedure. Yeah, you can do. You could do things like, suppose I have somebody who quite often one of the things we want to determine is whether there's kind of a pattern. Like, say I'm trying to decide whether to loan someone money. If I've loaned them money 3 times before, and each time they've been late but eventually paid it back, they actually might not be that bad a person to loan money to, because you will get your money back and you're going to get like lots of kind of interest fees, as compared to the person who has some other pattern, like they are hugely in debt from one bad financial situation. The partner got horribly sick and they borrowed to the hilt to keep them alive. So yeah, that's a reasonable use of CHR. In fact, one of the other big uses of CHR is that a company called Securities, which is one of the bigger Prolog shops, has an awful lot of CHR in their system that does things like they do clearing stock trades in New Zealand. So there are lots of complicated regulations about stock trading in New Zealand, and their system basically will confirm that your stock trade is legal, and confirm and then also automatically generates a GUI that gets the information you need for this particular kind of stock trade. yeah, there's actually out there somewhere a talk by Mike Elston of Securities about their use of CHR. Okay. Another kind of recognition use, and yeah, I should have started this thing, but it's too complicated. I can't start it on the fly. We did a Ludum Dare. I sometimes organize Ludum Dare teams. Ludum Dare is a large game jam, and I sometimes organize teams to do games in Prolog. Prolog, of course, is a horrible thing to write games in because it has no graphics, but that oftentimes pushes us to do really creative and interesting things with Prolog's power. So for one game, we used Snap, which is kind of like Scratch, as the front end. It's one of these drag blocks and build a game or a little interactive thing. You drew pictures. There was a pig and a wolf, and you drew pictures of houses, and the pig would hide in the house, and then the wolf would come and blow the house down, and you had to stay ahead of the wolf, so there was always a house for the pig. I wrote the recognizer for that in about 6 hours in CHR. And I just did it by it's a bunch of essentially simplification rules. That line, okay, there are 2 points. That makes a line. So there's a line. And this line and this line is almost vertical. And this line is almost horizontal. So I will replace this one with a vertical line. And I will replace this one with a horizontal line. And hey, their corners are nearby. So I will replace them with what I call a corner. And here's another corner. And hey, their corners their free ends are close. I can replace that with a box. And I do some similar things with a triangle, and hey, it turns out I have an upward pointing triangle that's the top of a box, and that's a house. So, and in fact, you know how it is with game jams. You get big ideas, and then you have to cut them back. And my big idea was that you're going to be able to draw all kinds of things, and it would recognize them and kind of replace your crude drawing with a nice drawing and then animate them, and there would be people wandering around. Of course, we never got there. But as a result, the recognizers actually has most of the guts to do a lot of recognizing a lot of different things. Somebody mentioned clips and forward chaining. This is a classic forward chaining problem, is to place furniture in a room in ways that would I say that it was a good application of CHR? Yeah, sure. I'd never been able to write that in anything else. In the context, you know how little code you actually can put out during a game jam. If you've ever been in one of those things, or a hackathon, it's just one weekend, and usually it's total chaos. So, yeah, the house recognizer was a lovely application, and I've stolen pieces from it for other things, which never happens with game jam code. Okay, so this is a little forward chaining expert system that solves the kind of traditional where to place the furniture in a room problem. design constraints. There's a commercial PCB, printed circuit board design checker that is written in CHR atop C++, I think. It is not atop Prolog. Okay. Well, you've got exercises coming up and there's stuff coming out. And then we've got Veronica Dahl coming this Saturday, and she's going to talk about using CHR to do to work on social progress. That's kind of our topic. So I'm really looking forward to that. Okay, I think it's time to go. All right, I thank you all. Sorry if this was a little confused. It ran short. I fiddled. Yes, it should be on YouTube. It's streaming on YouTube, and then we'll put it up as soon as I believe there's a little delay while they transcode it, and then it's up. Okay, thanks. Bye-bye.